Okay, so good afternoon. My name is Siqi, and I recently finished my PhD at the University of Toronto and moved to Munich last September to start my postdoc in Professor Engel Scholik's group at the TUM, Technical University of Munich. Thanks for having me today to the seminar series. We're happy to be here and share some of the results from my PhD research. The title of my talk is Neural Networks as Add-on Modules for Improved Performance of Robot Control Systems. Empowered by the advances in both hardware and software, autonomous robots are envisioned to become reliable human companions in various applications. We can visualize different robot applications over this 2D plot. The horizontal axis shows how much we know about the robot system, while the vertical axis shows the level of safety we wish to achieve. In traditional applications, robots are programmed to perform repetitive tasks in well-characterized environments. However, in more recent applications, robots are expected to operate in increasingly versatile environments that require continuous learning and adaptation. We can also visualize different robot decision-making approaches in the literature over this 2D plot. Classical control approaches typically start with a prior model of the robot, and by exploiting the system structure, we can provide different levels of safety guarantees. On the other hand, we also have data-driven approaches. In particular, reinforcement learning is the standard machine learning framework to address the problem of sequential decision-making under uncertainties. In contrast to classical control approaches, reinforcement learning can be applied when the model of the system is not known. However, providing safety guarantees can be typically more challenging. And recently, we see a trend where control approaches are integrated with data-driven approaches to improve the generalization and performance of robot decision-making algorithms while still preserving the desired safety properties. In one of our recent survey paper, we summarized the recent literatures into three categories. The first category is safely learning uncertain dynamics, where machine learning models are safely incorporated to standard control frameworks to improve performance. In this works, probabilistic or hard constraint satisfactions can be guaranteed. And we also have safe and robust reinforcement learning algorithms that encourage safe exploration in the learning process and achieve soft constraint satisfactions. Lastly, we have safety filter and safe certification methods that can be augmented to and thereby provide probabilistic or hard safety guarantees to learning controllers that were not initially designed to be safe. The work from my PhD generally falls under those two categories with a particular emphasis on neural network-based approaches. The goal of my PhD was to develop data-driven approaches that safely and efficiently exploit the modeling capability of neural networks for robot control applications. And in this talk, I would like to share three works from my PhD. And the first one is learning add-on inverse modules to enhance robot performance. The second part is on Lipschitz network adaptation to bridge the model reality gap. And the third part is on learning control barrier conditions to provide safety guarantees. We'll start from the first part. In this part, we consider trajectory tracking problems, which is part of different applications such as UAV-aided inspection, automated manufacturing, and autonomous driving. In these applications, high accuracy tracking is often required for safe operation and optimized performance. And due to the nonlinearities in the dynamics, as well as unknown disturbances, achieving high accuracy tracking can be challenging. In the literature, there are different approaches to achieve basic tracking functionalities. The most common one is PID control. Despite its simplicity, it can be shown in theory that perfect tracking cannot be achieved for arbitrary trajectories. On the other hand, we also have model-based approaches such as MPC LQR that allows us to optimize the performance of the robot given a dynamic model. The performance of those model-based approaches, however, are often limited by the accuracy of the model. And lastly, we have adaptive control and robotics control approaches that are targeted to address the issue of model uncertainties. But those approaches are typically restricted to systems with a particular structure or can lead to conservative performance. In our work, we consider the following setup where we have a black box robot baseline system that does not necessarily have a good tracking performance. With an augmented system with a neural network inverse module that adapts the reference sent to the baseline system with the goal to establish an identity map from the desired output to the actual output of the system. In contrast to other learning-based approaches, in our work, we've leveraged the existing controller available to the robot and used data to enhance closed-loop performance. This add-on learning architecture makes the overall approach more data efficient and also less prone to instability issues. Here's an overview of our approach. We assume that the robot baseline system is represented in the following discrete time control form. From control theory, we can show that if we are at a state xk, the input and output of the system can be related as follows. Here, f and g are nonlinear functions of the state x, and yk plus r is the output of the system, are steps ahead. The variable r here denotes the relative degree of the system, and intuitively for a discrete system, the relative degree is the inherent delay of the system, or the number of sample delays between applying an input to the system and observing a corresponding change in the output. Based on this input-output relationship, we can derive an inverse map to achieve exact tracking. And yd k plus r here is a future desired output. When the dynamics of the system is not known, we can train a neural network as an add-on module to approximate this inverse map based on system input-output data. Here's an illustration of the proposed approach. We verified the approach in quadrotor impromptu tracking experiments. And here the goal is to have a quadrotor track arbitrary hand-drawn trajectories accurately in single attempts. We first show the performance of the robot baseline control system. And if we augment the neural network inverse module, we can significantly improve the performance of the robot. And this performance improvement can generalize to different trajectories. We overall tested the approach over 30 test trajectories and observed that the add-on module led to an average of 62% tracking error reduction. Just to summarize, in this work, we propose a novel neural network inverse learning approach to enhance the tracking performance of black box robot control systems. In contrast to other learning-based approaches, the proposed neural network add-on module does not modify the underlying controller of the robot system and makes the overall approach more data efficient and less prone to instability issues. And the proposed approach can improve the tracking performance on arbitrary trajectories. In our paper, we also provide a stability analysis of the proposed approach, as well as additional theoretical insights to further improve data efficiency.
Siqi, do you mind if I ask a little bit more about exactly what you were doing in this previous slide? Yeah. So if you go back one more slide before your video. One more. Yeah, okay. So here, for the quadrotor, so you have some sort of baseline controller. In this case, I'm guessing that's doing the low-level attitude control. And your reference signal, is it like a desired position for the quadrotor? Is that what's going on?
We assume the baseline system for the quadrotor experiments, the baseline system is the PD position control, the full, so it includes the position controller as well. But the PD gains are not necessarily well tuned for arbitrary trajectories.
I see. Okay, so
yeah.
So your desired output though, it's like, so the desired output is like a position of the system?
Yeah, here's the position.
But like if you use like differential flatness for quadrotors, then you know you need to have up to like snap to be able to track a trajectory accurately. So yes. Is your inverse mapping essentially learning how to predict the snap or like the higher derivatives of the desired output, or is it learning the robot's baseline control system and understanding where that error needs to be tracked better? Like, what exactly is it?
So yeah, so in this work, we formulated everything based on discrete time. So instead of relating the input and the higher derivatives of the output, then we relate the future output like R steps ahead. That's how we account for. It's like translated to an inherent delay of the system in terms of like future output instead of the higher derivatives.
But then the neural net, so to apply this equation, UK equals F and N, you need the Y desired at some K steps forward into the future.
Yeah.
So where does that come from? Is that neural net predicting the future Y desired, or are you providing a Y desired future?
So in this experimental setup, R is for our system is actually 4, and it's sampled at like 7 hertz, if I remember correctly. So it's not like a long preview of the trajectory. It's only like 0.5 seconds ahead of like the current time. Yeah, so we assume the trajectory is given, or at least like a portion of the trajectory preview is available.
Okay, so the Y desired at K plus R is already known.
Yeah, we assume that is given.
Okay, cool. That makes a lot more sense. Okay, very cool.
Yeah. But I'm guessing you also need the K plus R time information from for the actual state, right? So, or do you only need it for the desired state, like desired output?
It only requires the K plus R of the desired one. The input will be the state and the future desired output.
Yeah, because this mathcal G, it is the sensitivity of the current control input to the future state.
Yeah.
So by these inverse mapping G, you only need the current state and the current control input to do G inverse.
Interesting.
Yeah, that's very interesting. Do you, for the theoretical guarantees, you have to assume that G inverse exists, right?
Yeah, we assume like it exists, and also this wouldn't be sensible for nominal phase systems if just directly learning an inverse. And then in that case, we have to do some approximate learning.
Also, I'm guessing in this paper also the whole neural network training is done online, right? I mean, the whole feedback and updating parameters is being done online. So how big is your neural network in this particular experiment?
In this first work, it was offline, but in a later work in the Lipschitz network, that one is online. And these networks are usually between 2 to 4 hidden layers, and neurons are like different, or ranges between like 50 to 128-ish.
Okay, cool.
Yeah, thanks for the questions. So now we move on to the second part, which is Lipschitz network adaptation to bridge the model reality gap. So in this work, our goal is to use online neural network learning to enforce an uncertain robot system behave like a predefined model. The reference model can be then used in a model-based approach to realize a desired control objective. We first show the architecture of our proposed approach. We consider a black box robot system with input U and output Y. We augment the system with a Lipschitz network adaptation module with the goal to make the overall system from input U up to output Y behave like a reference model. This reference model can be in turn used by a model-based controller or planner to realize a desired objective. This work generally falls under the literature of model reference adaptive control. And in contrast to typical adaptive control approaches, the proposed approach does not assume a particular parametric structure of the baseline system. And in contrast to other neural network adaptive control approaches, we guarantee stability via the network architecture design rather than relying on specific network parameter initializations or update rules. We similarly consider the robot system and reference models represented as control-affine nonlinear systems. If we know the dynamics of the robot, then we can derive an input correction map to make the robot system behave like the reference model. And when the dynamics not known, we design a neural network to approximate the input correction map. The parameters of the network are updated online to minimize the difference between the unknown robot system and the reference model output. In this work, we use a special type of neural network called the Lipschitz network, which is guaranteed to have a predefined Lipschitz constant via the network architecture design. Based on the system properties, we can derive a certification condition on the Lipschitz network module to guarantee stability. In particular, if we assume the robot system is finite gain L2 stable, then the uncertain robot system with the Lipschitz network adaptation module is stable if the following condition is satisfied. Here, L is the Lipschitz constant of the network, and gamma is the L gain of the system. This Lipschitz condition can be conveniently encoded in the design of the Lipschitz network. We show a numerical example to illustrate the advantage of the proposed Lipschitz network adaptation approach over a conventional network approach. In this example, we consider an unknown baseline system and a reference model given by the following state space models. The gray dashed line and gray solid line here are the input and output of the baseline system, respectively. The red dashed line is the output of the reference model. If we augment the Lipschitz network module to the baseline system, we can enforce the system output to be like the reference model. On the contrary, if we use a conventional feed-forward network, if the hyperparameters are not well chosen, then closed-loop stability is not guaranteed. And the plot below shows the performance of the Lipschitz network approach and as well as the conventional network approach for different choices of learning rate. If we use the standard feed-forward network approach, and there's typically an optimal learning rate at which the lowest adaptation error is achieved. And the system can become unstable if the learning rate is too high. For the Lipschitz network approach, stability is guaranteed through the architectural design. And in this particular case, we see the adaptation error is lower as we increase the learning rate. We demonstrated our approach using flying inverted pendulum experiments, where a quad rotor is expected to balance a pendulum in the upright position. The quad rotor here we use in our experiments is an off-the-shelf platform, where an accurate model of the onboard control system is not directly available. We first show the baseline system performance, which is an LQR controller designed based on a simple acceleration dynamics model. And due to the model reality gap, the standard model-based controller cannot stabilize the system. Now we augment the control quad rotor system with the proposed Lipschitz network. We can make the overall system behave like a reference model and thereby bridge the model reality gap for the LQR controller to successfully applied. This overall controller can tolerate moderate disturbances such as the wind and tap. And the same controller also allows the quad rotor to track circular trajectories while balancing the pendulum in the upright position.
These are really cool experiments.
Yeah.
Thanks.
We have been working for corridors for so long, but I think we are still afraid to stand so close to them.
It took a little bit of time to kind of get to know the system and get it working. Yeah. So to summarize in this part, we propose a Lipschitz network adaptation approach to make the unknown robot system behave like a reference model, which can be used by a higher level model-based controller or planner to realize a desired control objective. The proposed approach does not rely on particular parametric structure for adaptation, and stability of the approach is guaranteed via the Lipschitz network design. This was verified using flying inverted pendulum experiments. In the first two works, we look at. Do you have questions?
Can I ask a question?
Yeah.
Can you give like a more, I don't know, a qualitative understanding of why Lipschitz neural networks are so insensitive to the initial parameter choice, like the hyperparameter choice?
So yeah. So through the theoretical analysis, which is based on a small gain term kind of argument, we kind of can show that.
I guess whatever you think would help us imagine, like, okay, this is the reason why Lipschitz networks have so much more stable learning compared to like non-Lipschitz networks. Like the plot you said for feedforward networks versus a Lipschitz network, I mean, that was really interesting. It's like, yeah, this one, the one on bottom right. Yeah.
Are you asking why Lipschitz networks have Lipschitz constants, or why the Lipschitz constant is important to stability?
Why having Lipschitz constant for neural networks makes this learning so stable and like so well behaved, right? I mean, as you increase the learning rate, somehow they always improve the performance. Wait, the learning rate is the factor you multiply with the gradient, right? In the gradient descent?
Yeah.
So how come having a large learning rate is leading to smaller errors?
So this is more like we act, we kind of try to do faster adaptations in this case. But I don't think there is a general performance guarantee to this approach yet. But like we can in general guarantee that the overall architecture will guarantee stability, and then if we chose the learning rate to be high, that means like we adapt to the observed error quicker, and that's why we observe a decreasing trend. But it also depends on how good the overall learning is in general to achieve this kind of asymptotic behavior. But one thing we can guarantee from the architecture is stability.
And here you're comparing it with a fixed number of iterations of learning, or are you doing learning to convergence?
What does the x-axis represent here? Sorry.
Yeah, we just do online learning. So we're just like using a fixed window of data from the past couple of steps, or like 20 steps.
So when your learning rate is too low, you've basically not, the neural net hasn't converged to the solution.
Yeah.
Okay.
Yeah, so like generally higher learning rates, faster adaptation.
But there should be a limit, right? Because it's basically a nonlinear model. So if you have a very large learning rate, wouldn't it induce some errors?
I think she's doing linear system though here.
But neural network itself is nonlinear, right?
That has a Lipschitz guarantee, which means the small gain means that the closed loop is still stable. Is that correct? Did I understand that right?
Yeah. So basically with this Lipschitz condition, like even if the network weights are completely random, the output would still be bounded in some way, even though the performance may not be, performance is not great. But like if just doing the right thing, adapting the parameters based on the gradients, and it will drive the system to be closer to the reference model.
Interesting, because I mean, it still baffles me how increasing the learning rate always leads to lower errors, because in nonlinear optimization in general. For example, Adam and other nonlinear optimizers, they keep changing the learning rate based on the performance. So that's why they were developed for this. And here, even for large learning rates, you have like better performance. So that's interesting.
Yeah, and this is what we show from this example. For like more general systems, I think it would be interesting to actually study the performance guarantees of this approach.
Do you need to assume like a minimum phase system?
Yeah, here we also assume the system is minimum phase.
Learning gain sufficient.
Sorry, the voice was a little bit cut off, I think.
Because if not, sorry, what was that?
that way, as the internet might not be too stable. I think some of your words were cut off.
See, I might be on the wrong network. Yeah, I'm gonna reconnect on the Wi-Fi, would be better.
Okay.
Hi, can you hear me?
Yeah.
Ah, sorry. Yeah, I was on the wrong network. I was still connected to my lab, even though it's on the other side of the building.
Nice.
Yeah, okay, that's cool. That makes sense.
Yeah. I think I missed half of the comments you had before, but yeah, if you have more questions,
No
you can
worries, no
answer.
worries.
Yeah.
Yeah.
Yeah, so in the first two works, we look at how we can use neural networks to systematically improve performance of closed loop control systems. And then the last part is a newer work from our lab. It's on learning control conditions for providing safety guarantees to uncertified controllers. That can be, for example, a learned policy represented by black box models. And this work is in collaboration with Lucas, who will also give a talk later in this seminar series. In this work, we consider safety as state constraint satisfactions, and the safe set is represented by the zero-level set of a control bear function that is assumed to be given. And just as a quick recap, control bear condition intuitively is a scalar condition that is necessary and sufficient for showing positive invariance of a constraint set. If we consider a control-affine system, the CBF condition can be written as follows, where gamma here is a class kappa function. This condition generally ensures that the lead derivative of the CBF is non-negative on the boundary of the safe set. And instead of the safe set, the lead derivative is lower bounded, which constrains how fast or the rate at which the state of the system approaches the boundary. We similarly consider the quadratic program for safety filtering. Here, the objective function encourages the optimization problem to find a solution or input as close as possible to the raw input computed by the learned controller. And the constraint guarantees that the constraint satisfaction is achieved. As many of the learning works are motivated by the fact that we do not necessarily have exact knowledge of the dynamics of the system. And this would also be a problem to use this framework. In particular, we cannot directly compute the lead derivative if the system dynamics is not known. So in this work, we considered the case where the dynamics of the system can be decomposed into a nominal part denoted by F bar and G bar, as well as an unknown part denoted by F, delta F, and delta G. We further assume that the nominal system is safe on the constraint set and has a known control bear condition. We propose a Bayesian linear regression approach that exploits the structure of the CBF condition. In particular, we approximate the uncertain part of the lead derivative in the following form, which is shown in red, which holds a particular basis function, which is a composition of a Lipschitz continuous function and the control bear function. Given this structure, we can derive a lower bound in the form that maintains the original CBF condition structure. In this work, we update the BBLR model online and use the learned CBF condition to filter unsafe inputs. Here, the first term is the estimated lead derivative, and the second term is the bound on the lead derivative error. And the first term on the right-hand side is the class kappa function associated with the nominal system. And the second term is the bound from the learning component. And this condition generally guarantees that the ordinal uncertain system can be rendered safe. We illustrate the proposed approach with a simple pendulum example, where the goal is to swing up the pendulum to the upright position while not going over. Here we show the response of a baseline uncertified controller. If we use a safety filter designed based on the nominal system, then we can guarantee safety, but the performance is conservative. And if we use the learned BBLR safety filter, we can certify safety, but not significantly jeopardizing performance. And the overall performance of the system with a safety filter is similar to the case where we design a safety filter directly based on full knowledge of the system. So as a summary in this work, we propose a Bayesian linear regression approach that exploits the structure of CBF conditions and can be used to certify safety for an uncertain system. And this approach was demonstrated using an inverted pendulum in simulation. I believe Lucas will also talk about this work more in detail and also our follow-up work, which we are working on right now.
Cool.
Yeah. Yeah, do you have questions for this work?
Yeah, you had some, so you've got unknown and uncertain dynamics in this?
Yes.
Oh, sorry, at least uncertain dynamics.
Yeah,
So in this case, what sort of uncertain dynamics have you added?
So we assume this is like additive uncertainty. So we have a nominal part and then like an unknown part is added to the nominal components. So like
Cool.
F
And do
bar,
you assume some bound on the maximum amount of this delta F and delta G?
yeah, we do need to know a bound, which is kind of boiled down to the lead derivative error to guarantee that this is like kind of certified in a robust way.
And then does that bound like change? So why do we need the Bayesian linear regression learning? Like where does that come in?
So if you look at the condition on the bottom right, so there's a delta term subtracted on the left-hand side, and specifically the error in approximation. So if you know more about the lead derivative of the true system, and this part will shrink, and this comes from the uncertainty or the probabilistic formulation of the Bayesian linear regression model.
But then if it comes from a probabilistic sense, then isn't your safety guarantee also probabilistic?
Yeah, yes, it's with high probability and this condition will be satisfied.
But okay, so maybe I'm not too familiar with Bayesian learning, but then don't you need to like get like where's the don't you need to like learn or converge to some level before you can say that you have high probability confidence on these bounds? Or is the bound always correct?
So it's always the worst case bound. So so initially this delta will be the the contribution from the uncertain part, and over time this will decrease if we know about the system better. So this is like we always consider like the worst case scenario when we apply this approach.
I see. Okay. But you're directly learning the lead derivative L delta F and L delta G of H.
Yeah, we directly learn the kind of two terms associated with L delta F and L delta G. Kind of the lead derivative of the control function with respect to delta F and delta G.
And your basis function is the phi of J. Does that have to be tuned for your specific system, or is that like a set of like, you know, polynomial bases or something like that?
Yeah, in this first work, we just use polynomials for the basis function.
Cool. Then my question here is sort of from what it looks like in the expression you have, it's phi of H of X, which means it only depends on the H value at any, like if you've got multiple X's with the same H value, your lead derivative terms are also going to be the same. Or do you have phi that depends on X as well, like directly on X?
Yeah, this is a very good question. Like expressiveness is kind of a question of this form. Yeah, so like in this first where we can just consider online approach, and it's like a small generalization of the state space. So this did not occur as a bigger problem, but if we move to like offline learning, this could be a problem in generalization. Basically, like all the states are not necessarily distinguished if they have the same control bearer function value.
Yeah.
So now we're kind of working on an extension to mitigate this problem by decomposing the learning Lie derivative in a different way, rather than rely on this composition.
Right. Yeah, because I've been thinking about a very similar problem, and that's the problem that I've been having. That as soon as you make it phi of x comma h, then the size of the data buffer becomes huge. Essentially, it depends on the entire location and state, and then you can't really learn unless you go back to the same spot as before, right? Because if you're always in a new part of the state space, then what exactly are you learning from past data? So
Yeah.
that's a challenge that I've been having, and it'd be interesting to see how you guys tackle this.
Yeah, we have also been thinking about this. It's kind of more challenging in the actually like in the offline scenario. Generalization is kind of actually harder to guarantee.
Yeah, I mean, even in like an online scenario, like I don't know exactly how you would represent phi of x comma h in a way that it's, you know, your learning is reasonable, even if you were to do it like locally. I'm not sure. But, okay, very cool.
Yeah, hopefully by the time that Lucas presents, he can share that part of our story.
All right, I'm gonna hold him to it.
Yeah. Okay. I just have a couple conclusions and slides. So yeah, just as a conclusion, so in my work in my PhD, we explored how we basically explored learning-based control approaches that combine control theory and machine learning, and demonstrated in experiments how we can use data to improve performance of classical control systems, and also how to leverage control theory to guide safe and efficient implementations and provide stability guarantees to learning-based control techniques. And there are a few interesting extensions that some of them are kind of as will be my postdoc research direction. So the first one will be incorporation of perception and semantics in the controller design. Another interesting direction will be further investigating the characterization of similarity for nonlinear robot systems that can be efficiently estimated using minimal data online, and also extending some of the approaches to a broader class of robot control systems, such as systems with hybrid dynamics. And just lastly, I would like to highlight a few efforts from my lab, which is around the safe decision-making in robotics project. We started off as a survey paper on safe learning in robotics, where we summarized safe decision-making techniques from both the control and the reinforcement learning communities. And as a follow-up work, we proposed a benchmark suit to compare control and safe reinforcement learning approaches on the same basis. And we have also been organizing workshops and competition around this topic of safe learning control. And we'll be generally very happy to hear your feedback and comments on the topics, or potentially collaborate or co-organize some of the events.
That's really cool. Yeah, it'd be awesome.
Last advertisement. So we're hiring. So if you know anyone who might be interested, let us know. Yeah. Thank you very much. Sure. Yeah.
Thank you. That was really nice.
Well, I see that you're open for exchange, so that's something which.
Yeah, I'd love to come to Germany for a few months.
Yeah. So just send us an email, and we can organize a lab visit.
Yeah, that'd be awesome.
Yeah. Yeah, that's all from my side.
Cool. I'm curious to see a little bit more about, or to hear a little bit more about what you're doing with the perception stuff. You said you've started to get into perception. I'm curious which directions you're interested in.
Yeah, so one project we're currently thinking, or just like starting to work on, is how to incorporate semantic understandings of a scene to or how to represent that as a control bearer function for safe control. So for example, if we want the robot to move a cup of water over a laptop, semantically, we don't want the robot to pass the water over the laptop. So how do we encode those kind of semantic constraints in a computable form for safe control?
Interesting. Okay, so, but then where's the specification that water plus computer is bad? Where does that come in?
I guess that's the first step. We'll assume that some form of specification is known. For example, the robot knows, okay, one object over another object is where some positional relationships are considered unsafe. And then from vision, you can use the scene graph generation, for example, to understand what are the spatial relationships and integrate that as ACB5 constraint.
I see.
Yeah, it's something we're kind of exploring right now. Yeah, it's kind of still earlier. I mean, there's a couple more recent work is kind of in related areas, like the latte work. I'm not sure if you have came across that work.
What is this work?
So it's also from TUM, where they have this language input and to tell the robot to modify its trajectory based on language input from human operators, like move slower or move closer or further away from objects. There's some interesting directions, like I guess all targeted towards how to interact with robots in a more language-based or natural way.
Oh, I see. Okay. So you're sort of interacting with the robot and it understands. So you're giving it corrections on what it's currently doing, and it knows how to parse that into control inputs.
Yeah, kind of translates words or language-based specifications into finally like defining a condition in the input space.
Very interesting. Nice.
Good, yeah. I'll let you know if we have more results in that direction.
Oh, yeah. I know Lucas was talking to us about the gym that you guys are building for testing out reinforcement learning techniques. And yeah, I'm sure he's going to talk about it as well. And I'm excited to hear where that's going and what sort of things you're going to be trying out on that. Yeah.
Yeah, that's also one ongoing project right now. Yeah, I'll keep a note, let him know.
Very cool. Hardik, any questions? Any questions for us, Siqi?
Don't have anything in particular yet, but like it'd be nice if we can organize like lab between two labs, like a short discussion meeting, so we can all talk to each other about our own projects. That'd be interesting.
That'd be really cool. Yeah. I'll definitely talk to Panagu, our advisor, and see if we can arrange something either between students or just across or across the whole lab, like with the professors as well.
Yeah, and yeah, if some people from your lab are going to ICRA or yourself is going to ICRA, could drop over or drop by in Munich.
Yeah. For sure. All right.
Are you going to ICRA?
No, I'm not going to ICRA, but I think Mitchell is going to be going to ICRA. Mitchell is one of our lab members. He works on a lot of adaptive control.
Okay.
And so he has been working a lot on fixed time adaptive control. So that's also something which our lab is really interested in, which is like adaptation or learning in like fixed time, because we want to be able to say that, okay, we will finish task in a given time. And then if something was unknown, we want to be able to learn the unknown things in finite time so that we can finish the task in finite time. So that's also a topic of interest for our lab.
Yeah, I
But
think
sorry, go ahead.
No, go ahead.
Yeah, in general, I think we have also been thinking more about safe learning with perception, like taking into account real sensor noise and estimation errors into the control, and then guaranteeing safety, and then ensuring that we finish the task in like more optimal way. Yeah,
that's also like I think what Lucas also interested in his PhD thesis. It's like not assuming perfect state output, state feedback.
Yeah.
Yeah, we were happy to like discuss those topics further.
Nice. Yeah, we'll definitely we'll try and set something up so that we can dive into open questions a lot more.
Yeah.
All right, very cool. Incredible timekeeping. And it was really nice to talk to you. Nice to meet you too, Veronica. Hope to see you guys sometime.
Yeah.
And if you guys are ever coming around towards Michigan, please do come and visit.
Yeah, we'll do. And thanks a lot for inviting me.
Yeah, if you guys are coming for
talking.
Iris is going to be in Detroit, so
Oh yeah,
in October. Yeah, it's like half an hour away or 45 minutes away. So
cross fingers, working on those applications.
2 weeks.
Yeah, we'll see. Yeah.
All right. All the best. Thanks, guys.
Great, thank you.
Bye-bye.
Bye.